Vector analysis is a potentially much broader topic than what I'm going to be looking at here, and it's potentially can get really complicated as well. But the thing that I'm focusing on that I think is kind of the core of the analytical methods for this class is the idea that if you have a vector equation, you can basically take that equation and apply it to the components. So in the first key concept, it says there, this is specific to vector addition. If C is equal to the vector sum of A and B, then you can say the x component of C is equal to the sum of the x component of A and the x component of B. And similarly, the y component of C is equal to the sum of the y component of A and the y component of B. It turns out that can apply to other equations as well. So maybe just as a quick example, maybe a couple of them, if instead I had said that C was equal to A minus B, and I asked, well, what does that imply? Well, I would be able to claim that the x component of C would be equal to the difference of the two components. Since I'm saying vector C is equal to the difference of these two vectors, the same holds for the components. And you can work this concept into mathematically. One might say any linear combination with vectors. You could do this, but what that really means is, like, let's say, for example, instead of just subtracting two vectors, let's say I said A minus 2b for some reason, then the x components would do exactly the same thing. So C sub x would be equal to A sub x minus 2b sub x. And similarly for the y components, you could make the same claim. And that can pretty much be done with any simple linear equation that involves just adding or subtracting and possibly multiplying by numbers. And so when I say a vector equation is a guide for component equations, it basically means you've got the vector equation, just write the same equation with either the x or the y components, and you have another true equation.